This is lab class number 12. Extremely important lab class, because now we will be showing it to you how the actual clean room class 1000/10,000 looks like. Okay. Now, this particular lab class we are just focusing in introducing to you how the clean room looks like, what kind of wet benches are there where there is only acid or you can use only solvent. Then we will be looking at the biosafety hood, then we will be looking at how the lithography room looks like. Okay. Then we will be looking at what kind of HEPA filters are there, and we will be looking at the incubator. So, a very important laboratory component for you to understand, and slowly and gradually we will also teach you how can you actually use electron beam / thermal evaporator, and we will be demonstrate you how it can be used in detail. We will be also showing it to you how can you use oxygen plasma system for bonding PDMS with glass. Alright. So, not only just giving you exposure for the actual or conventional clean room facility, but also showing it to you the equipment within the clean room. That is my idea, right. But for this particular lab we will be taking you or giving you a tour that how the lab looks like more or less. Okay. And you will see that lithography lab in particular will be of yellow color compared to other part of the laboratory. The reason is that because in lithography section we will be using a photoresist, and photoresist is sensitive to the UV light. So, even the tube light will expose the photoresist, and to avoid that we will be using the yellow color light. If you have seen in old movies, right, there is a red light, the room with red light, and the photographer is like exposing or curing the negative this photo so as to develop it, isn't it. So, why there was red color light? Because the photosensitive material that was used for capturing or developing the photograph, right, should not be exposed to UV, and that was the reason. So, similar concept, but now we are using at a micro level or a nano level, and that is why we have to use a yellow room. So, we will be showing you about for around half an hour. So, please look at it thoroughly, right, and like I said, slowly and gradually we will also show it to you the equipment within the clean room. Alright. So, till then you have if you have any questions, always feel free to ask. You can also simultaneously look at the YouTube videos. You see, you will have lot of information about how the clean room looks like, what are the class of clean room, right, and etc. Okay. So, that will be the end of this particular lab class after he shows this particular facility. And I will request my teaching assistant Anil to give you the lab tour, and I will see you in the next lab class. Bye.
Hi, welcome to this course. This module covers something very interesting. As you know, this course discusses about sensors and actuators. You would have covered or you will be covering as part of this course design of sensors, the fabrication techniques involved in making such sensors, what is the difference between sensors and actuators, how these are interfaced with electronic systems to make interesting systems that can be used for real world applications, how biological applications can be implemented using this, and such vibrant ways in which sensors and actuators interact with the real world you would have covered. In this module, we are going to see one very core aspect of sensors and actuators, which is fabrication of sensors, correct? Now, for sensor fabrication, as you would have understood by now, it is very important to have a very clean environment to avoid contamination of the fabricated sensor. For this, people use clean rooms throughout the world in all fabrication facilities. Clean rooms are classified as based on the number of particles of size greater than 5 microns per cubic feet. So, if that number is less than 1, it is called a class 1 clean room. If that number is less than 10,000, it is called a class 10,000 clean room. Most of the time in India, we usually have class 1000 clean rooms or class 10,000 clean rooms. For big companies like Intel, TSMC, Taiwan Semiconductor Manufacturing Company, they even have class 1 clean rooms where they make high-end processor chips, as you would be aware. All of you would be aware of Intel Core i7, i5, i3 and all. All these are chipsets that are fabricated from such facilities, and depending on the criticality of the process that is involved, they might even use a class 1 clean room. Today we are seeing one such clean room that is being developed here at IISc in Department of Electronic Systems Engineering. So what I will do as part of this module is show you how overall a clean room looks like, what are the protocols followed in going into such a clean room that will eventually fabricate the sensors that you have covered. Okay, so as and when you enter, this is what you call the gowning area or the entry area into the clean room. So here in this cupboard, which is used to keep the gowns, clean room gowns. So right now what I am wearing is just a lab coat with head mask, face mask and gloves. Now right now we are not operating the clean room, and we have not fully maintained the class of the clean room. So for that reason, right now it is okay to go into the clean room in this way, but once it is fully operational, we are doing this so that you understand how small things come together to form a good establishment. So as you enter, clean room gowns will be housed in this cupboard. So here it's just like another cupboard, but just that the material and all is made for a clean environment. So you can keep the gowns here, and other things like head mask, face mask also will be kept next to it. So this is the gowning area. So if you can see, yeah, so this is a separation which you can see that separates the gowned person from the ungowned person. So when you are not gowned, you stay here, and after you finish, once you have completed, you come here. So the protocol is that you enter the area. First you will put your head mask, face mask, gloves, head mask, face mask, gloves, and then you put your clean room shoes and come into this separation. Okay, and then you can may or may not choose to wear the gloves, but head mask and face mask is compulsory before you come into this. Then you come in, you take your clean room gowns from here, put it on, then you are ready to enter the clean room. So there will be for you to hear properly, we have switched off the circulation here. It will create a lot of sound. That circulation is what maintains the particle count in the clean room. Okay, then this is the door through which we will enter. So this, once you are ready, you can go in like this. So now you have seen how you gown and you enter the clean room, right? But now you are going to do a scientific research work there. It is very rare that you will go inside a clean room without carrying anything. Either you will have samples or you will have some notebook to write down things. Here two things are there. One is samples that you carry. You should make sure it is your own responsibility as a person who is working in the scientific field to ensure that your samples meet the cleanliness requirements of the clean room to which it is taken. So you should make sure that your sample is thoroughly cleaned. You should not have any contaminating particles, no dust particles and all, as much as possible. That is regarding samples. Now about notebooks. In clean rooms, usually special type of papers and notebooks are used. They are called clean room notebooks. I will show a clean room notebook in another session. So clean room notebooks and you should not use gel pens usually. You should use ball pens to write on that notebook, because gel pens also add contamination to the devices. Okay, they will enter the air and cause contamination. Or ink pens also, for that matter, are not allowed. Only ball pens and clean room notebooks. So now the point is that you cannot simply enter the clean room like this, carrying your device and your clean room notebook. Okay, this is because there needs to be a proper separation between the inside of the clean room and the outside of the clean room as much as possible, because we don't know what foreign particle might be there in the stuff that you bring. So for that we have a separation chamber. It's called a pass-through chamber, which we will see shortly. Now you can see the pass-through chamber. Okay, so this is where what it happens is you keep the items that you want to bring in, you keep them inside. Okay, so the thing is, you press the button and you open the door. Okay, and then you can keep your things inside. Okay, and then you close the door. So the thing is, why? Okay, when you look at it, you might think that, okay, this is simple. What is this? This is just a door. Why do you want so much sophistication for this? So the idea behind is, this door has a door on the other side, correct? The other side is the proper clean room environment. This door has a protection that it can only be opened from one side at a given time. So the moment you press this key, and open it, the other side get locked. So you keep your item inside, then you close it, then only can you open it there. So this way, if it's a normal cupboard, if both these doors are opened on either side, simply dust from the entrance will simply go inside. So this is the protection for that. So that is why it's called a static pass through chamber, that will reduce the contamination that might enter the clean room. So these are the things, these are small things which you may not come across, which you may not hear about, that are also part of a fabrication process. You might be making extremely mind-blowing designs, very innovative structures, but then if you can't fabricate it with that cleanliness or that finesse, it will not be useful to use a sensor. So that is why we are going through each of these small things, so that being a scientist, you also work as a responsible scientist. You have to be responsible for your work, and you also have to be responsible that you don't affect other people who work in a clean room. This is like a shared facility. It's not your own property. You are coming in to do your work, but when you do your work, you should make sure that you don't affect others. That's why these protocols and mechanisms are in place across the world. So this is the overall way in which you enter the clean room, you bring stuff inside. Now we will go inside. We have now entered the clean room. Okay, this clean room is something special. It's little bit unique compared to other clean rooms in that in this clean room we also have a biology section which we use to immediately test the sensors that we have built with biological specimen. Okay, so there is a main room which is where I am standing right now. There is a bio section which we will see shortly, and there is a litho room with yellow light, which also we will see shortly. These are the three main areas. Okay, so litho room is for the optical lithography, which you might have covered in the course, where the litho machine or the mask aligner machine is kept, and this room is where we do other processes. Okay, when we come to other processes, I need to tell you how in a simplistic manner you can look at microfabrication. As you know, this course covers microfabrication for making sensors and actuators, correct? Microfabrication can fundamentally be broken down to three processes. One is an addition step where you deposit material, be it metals, insulators, anything. Next, the second step is a patterning step where you make or imprint some kind of pattern on this deposited material, which is in turn on a substrate that does the patterning. Third is the removal step or the etching step, where you remove the unpatterned or the pattern, depending on the photoresist that you have used, material from the substrate. So these are the main three processes in microfabrication. But for each of these processes you use different techniques. Okay, for addition, which is the deposition of material, you can do sputter deposition, you can do E-beam evaporation or E-beam deposition, you can do thermal evaporation. So these are different techniques to deposit material. There is chemical vapor deposition, physical vapor deposition and all. In this main area, we will have E-beam evaporator and thermal evaporator systems, and that is the addition part of the addition process. And behind me you can see wet benches, which are used for wet etching of patterned substrates. Okay, these are the two main equipments or systems that are there in this main bay. In further modules, you will actually see the operation of these videos, if time permits, operation of these systems, which is the thermal evaporator, E-beam evaporator, if time permits in this course. Okay, this is one section. Next we will see what does this wet benches do in a short video as part of this module. So as I have told you that wet benches for wet etching and for cleaning processes happen in this main room. So these are two wet benches that we have. This is acids only bench, as you can see written on the wet bench, and it is, you can see that wet bench is written. This is a wet bench, and this is solvents only bench. Okay. As per safety protocols, acids and solvents must never come in contact with each other, because that is dangerous. Okay. That is why we have separate benches for acids and solvents. Okay. So now what happens in these benches? These benches are primarily used for two things. One is wafer cleaning. When you take a substrate which forms the wafer, when you take the wafer, okay, that is a substrate for a device fabrication. So that wafer first, before you use, has to be cleaned thoroughly. There are different types of cleaning, which is piranha cleaning, RCA cleaning, RCA1, RCA2. So these are standard cleaning procedures that are usually carried out. Okay, they have their own fixed concentration proportions, etc., which will be covered or would have been covered already in this course. Okay, so acid bench and solvent bench has to be separated. One use is the cleaning of the substrate, which is the wafer. Wafer can be silicon wafer, silicon insulator wafer, glass wafer. It can be a lot of different wafers. It can even be a gallium nitride wafer. Different types of wafers are there. Now, cleaning is one thing. Another thing is etching. Etching in the sense, suppose you deposited gold on top of your substrate, then you patterned it in lithography. There was a pattern formed, and then you want to take the pattern out. So lithography only forms the pattern. It does not remove material from where the pattern is not formed. You bring that wafer here, then you etch the gold. So gold etchants are there, standard etchants like gold and chrome, and gold will not be deposited as just gold. Gold will be deposited as chrome gold. First a thin layer of chrome, let's say 30 nanometer of chrome will be deposited. On top of that, your required thickness of gold, which is usually around 200 nanometer to 400 nanometer gold, will be deposited on your substrate. Why chrome is deposited? It is for stiction or better adhesion of the gold onto the substrate. Gold alone will not stick properly onto your substrate. That is why chrome gold is used. Now that we have used chrome gold on the substrate, you have patterned it, you need to remove the gold and chrome from where the pattern is not formed, right? So first you remove gold because chrome is below it. Remove gold with gold etchant, which is usually potassium iodide, Ki, and you remove chrome with a chrome etchant. So these two etchants will be kept here. Okay. Likewise, there are etchants for different things, or you might even use a lift-off process, which does not require a etchant for a specific material, but requires only acetone and IPA that removes the photoresist. That is separately a lift-off process which will be covered. So for lift-off processes or for etching also, these benches can be used. Okay, and you understood why. So as it's, let's say for silicon dioxide etching, you use HF. Okay, so for hydrofluoric acid, buffered hydrofluoric acid is also used for cleaning the wafer. A lot of things are there. So if the wafer you take, silicon wafer you take, it will have a small layer of oxide on top of it. Suppose you want to remove that, you use HF. HF is a heavily dangerous chemical to handle. So there is specific operation protocols for using HF itself. So HF is an acid, hydrofluoric acid. So that will be stored here. So these acids will be stored below in these areas, which will be labeled properly. So you might not have seen it, but there is a container below where the acids will be stored. So the chemicals will be stored just below the bench itself, and this bench is right now not switched on. So so as you know, you are handling chemicals, right? So when you add multiple chemicals, the chemicals will react. There might be fumes. Okay, water vapor might get created. So you have to be careful. You need to wear face shield and all, and lapel and everything to work on this bench. Right now we are not directly working on the bench. That's why I have not worn the PPE. What is PPE? Personal protection equipment. You need to wear personal protection equipment before you work with these benches. Okay, now I told you that fumes might get formed when you work with these benches. So these benches also come with an inbuilt HEPA filter, or a filter that sucks in air at a high pressure, so that inside a small high pressure is maintained, so that the fumes are sucked in. So it does not escape this side, so that if you are working like this, the fumes go that way and does not come this way. Okay, so there is switch for light. So you can see light has come, and the next button will switch on the filter. When I switch on the filter, you will hear the sound with the filter switching on. This is the sound of the filter switching on. We also have a meter which I will show you shortly. There is a meter on top of this bench which starts with zero pressure, and as and when the filter starts operating and reaches a stable point, it goes to a higher pressure and stabilizes there. That change we will see shortly. So this is how the wet bench works. So now when you have to work, you lift the glass slide only up to how much ever you require, maybe around this much, and there are outlets for the discard, and these holes are there through which all the liquid will go in. Okay, that is the overall operation. Let's see how the meter works. So you can see the meter here. Right now it is in zero position. Okay, so I am going to switch on the filter, and as I switch on the filter, you can observe that the pink or the orange indicator will change. So it is moving, slowly moving. The pressure is in millimeters of water. Okay, it is going and it stabilizes at around 9.8. Okay, so that is how this works. So this shows that there is a positive pressure inside, and the wet bench is operational. This is how you use a wet bench. So we have seen the wet bench which is next to me here, and now we are seeing, so this is a module, filter module, HEPA filter module. Apart from the overhead filter modules that are there for maintaining the clean environment of this room, we have a separate filter modules also dispersed throughout this room for maintaining the air quality. Okay, so I have connected with the power. So this is a filter. There is filtering mechanism inside. It's a very sophisticated equipment which needs to be maintained thoroughly. So if when I switch on, you will hear the filter turning on. As you can see, it's creating a lot of sound. So that is why I am just switching it off. That is why we are recording presently with things switched off, so that you can hear me properly. Imagine around 10 of this switched on parallelly, so that much sound will be there. So that's why we have switched on for a short time for us to show you this facility. So this is HEPA filter. What is HEPA filter? High efficiency particulate air, HEPA filter. Now we have seen the HEPA filter. We will go to the biology section, which I told you before, of this clean room. So we will go inside the biology section. We have entered the biological section within the clean room. The main equipment that will be there in such a biology section will be usually an incubator for growing the cells and maintaining cells, and a hood. What hood? Biosafety hood, biosafety cabinet, that is used for processing the cells, tissues, etc. Okay, I think you have already covered in detail how a biosafety cabinet generally works, and you have seen one biosafety cabinet in the other lab. This is another biosafety cabinet. The operating principle is everything is same. Before you use, you need to switch on the UV light. I am switching on the UV light now. So now UV light is switched on. Before you use, you have to switch on the UV light and leave it for like 15 to 20 minutes for sterilizing and killing all bacteria inside. Okay, once that is done, before you start work, you switch off the UV light. You cannot work inside the UV light because it is carcinogenic. Then you switch on the lights are switched on. Okay, now your lights are switched on, so you can see inside there are these vents. That is for air circulation. What happens is air gets sucked in and gets recirculated through this top filter. Again another HEPA filter is there. So I am starting on the air. You can see the air being circulated. So if I lift it up, you can see this. So it is actually circulation is from inside, it is sucking. Okay, now you have to work with the air on, and you can see the mark here with, I think you have covered already. This glass should always be at or below this mark. Okay, you can see the lights are there inside. Now how to work? I'll also talk to you about the protection that is there in this equipment. Let's say I have told you that, let me switch on the air now. I have told you that the UV has to be on, correct, before using, and you have to switch it off before you start working. So the light is on, the UV light is off, the filter is on, as you can hear the sound. Then you are ready to work. How you will work? You have to lift it, the bare minimum that you need it to be lifted. Put your hands inside, and with minimum movement you have to operate all the equipment and samples that are inside. This is the way you should work. And once it is over, you have to wipe your hands with ethanol, that is a disinfectant, and then close the hood and switch off the light and fan. For now I have shown the light to you so that it is visible for you. So this is how a hood works, biosafety cabinet for processing tissues, cells and all. Why we are having such a facility inside a clean room is, as and when we make the sensors, we can do a preliminary testing here itself. This is something very unique about this lab, because most of the clean rooms across the world have strict protocols, but they are used for VLSI fabrication. What we work on is MEMS fabrication and sensors and actuator fabrication, where we very often have to deal with biological samples for testing. So MEMS fabrication and VLSI fabrication are two different separate streams, though the processes involved are same. So VLSI most often would not have to interface with biological samples, but MEMS devices constantly interact. So there should be a facility where we can quickly test our fabricated sensor in the most cleanest environment and test it out, preliminary testing, then you can take it out and test it in other labs, because finally it has to be used in a normal setting, right? But then you need, for you to characterize your sensor, you need to test it in the environment where it was made. For that we have made a biological section like this. Okay, next we will see an yellow room. We have seen the biology section of the clean room here. Next we are going to a very important heart, actually, if you look at it, of the clean room, which is the yellow room. Why we are using yellow room? This yellow room is used for optical lithography. Before I go, let me switch on the yellow lights. You can see the glass inside, there is yellow light. Before we go in, let me introduce you why this is required. So optical lithography is what we perform to pattern, correct? I have told you. Optical lithography is fundamentally done using a material called photoresist, which is a photosensitive material that is coated on top of the deposited material. The photosensitive material is spin coated, then hardened and then exposed to ultraviolet light. So photosensitive material is sensitive to ultraviolet light, and under the influence of ultraviolet light, it changes its properties depending on where the mask is exposed or not exposed, correct? Through the mask, the ultraviolet light will fall on the photoresist. So some parts of the photoresist will get exposed to ultraviolet light, some parts do not. So after we spin coat, before we use a mask and a UV light source, you need to be able to handle the photoresist, right? So what do we need for such an environment? Yes, we do not need ultraviolet light in that environment, because the photoresist will get blanket exposed. For that we use yellow light, which does not affect the photoresist. So you coat the photoresist, use the photoresist, everything in a yellow light environment. Then you take it into the lithography machine, which is usually called mask aligner, and then you expose it to UV light. Okay, we'll just quickly go in. We will have a separate session on mask aligner if possible in this course. Otherwise, we'll just see the yellow room inside now. So I have entered the yellow room. As you can see, everything is yellow. Yellow light is falling on me. I'm sitting inside the yellow room. In another video, we will try to show you the equipment here if time permits. But generally, what are the three main equipment that will be there in any yellow room? The beast in the room, the main guy in the room is the mask aligner, or the mask aligner system, which is the lithography machine, which will have ports to input the wafer, one port to put in the mask plate, and then UV light source and laser source to expose the wafer through the mask. That is the mask aligner system. What does it do? It aligns the mask along with the wafer or the substrate and then exposes it. Okay, but before we do that, we have to spin coat the photoresist, right? So you will use a spin coater machine that rotates at unique RPMs, fixed RPMs like 4000 RPM, 5000 RPM, 6000 RPM, and then you spin coat after dropping the putting the photoresist on your substrate, and then you switch on the spin coater. It will rotate and uniformly spread the photoresist on your substrate. So spin coater is required. Then you need, if to work with the spin coater, you need a workstation, pathology workstation. It is just like the hood that we saw, but just that it will not be that sophisticated. It will have basic protection and a fume hood. So the photoresist and all are they have unique smell, and many times many chemicals are a little bit carcinogenic and all. So the fumes you should not breathe in. So it will have a fume hood to take out unnecessary fumes that are formed inside. So it's always advisable to work with photoresist material and other materials inside a fume hood. You stand in like the one we saw before. You stand inside the fume hood and then work with it so that the fumes get sucked in and you are not affected much. So that is required. So you use the fume hood, you put the photoresist, you take the wafer, okay, which is having the photoresist drop, put it on the spin coater, or you put it on the spin coater and then drop the photoresist, switch on the spin coater, it will uniformly deposit the photoresist on the substrate. Then you take it out. You have to do a lot of heat treatments before and after you do photoresist coating. So let's say you bring in the wafer, you need to first dehydrate it so that there are no water particles or water molecules on your substrate. So first you keep it on a hot plate, on the wafer on a hot plate, so that for like 130 degree, 120 degree, depending on what is your process parameter, so that it will have a dehydration. So that's called dehydration bake. Then you put it on the spin coater, you put your photoresist, and then you spin coat it, then you heat it also again for a minute. It's called what you call pre-exposure bake, because before you expose. So the pre-expose, that there will be a small bake, it's called baking of the photoresist. Then you take that into the mask aligner system, you align it, okay, expose it to UV, take it out, and then you have to develop it. So development is just like in olden days people used to develop photofilms, right? It is just like that. When UV light falls on the photoresist material, some part where the light falls on, the material gets developed, other parts material gets changed, chemical property changes, other parts it will remain same. So when you develop the photoresist, depending on the type of photoresist, there is positive photoresist and negative photoresist. Depending on the type of photoresist, the part that was exposed to the UV light remains or gets removed by the development process. This development again involves chemicals like MF26A, which are the usual developers that are used. There are a lot of photoresists like S1813, like AZ4562. These are all standard photoresists. The numbers denote the micron of thickness of photoresist that gets formed when you coat it. Let's say AZ4562 is a type of photoresist. In that 4562 means that 6.2 micron, the last 62 is 6.2 micron will be the photoresist thickness when it is rotated at around 4500 rpm, that is 4562. Okay, and so like that we have S1813. So like that lot of photoresists are there. For each of the photoresists you have different types of developers. So you use a developer solution and then you develop it. So this development will also be carried out in a hood, like I told before. After you develop, you again have to use a hot plate where you hard bake it. It's like whatever photoresist remains, that will be hardened on top of it so that it can be used for further processes like etching. Okay, so what are the main equipment that will be required in a yellow room? You need a workstation or a workbench or a fume hood you can call for your photoresist coating, baking like dehydration bake, pre-exposure bake, etc. Then you need a spin coater machine, hot plate as I told. Then you want the mask aligner system, okay, and then a bench for development which can be the same bench. This much is required for you to do the lithography process. Now why we need to do a hard baking of the photoresist? This is because let's say there is a subsequent process. I am having a gold deposited again. I am removing after the photoresist exposure, I will use gold etchant. So wherever the photoresist hardens and remains, that part below that gold will get protected. Everywhere else the gold and chrome gets removed. So once that process is over, you can remove your photoresist through like a acetone IPA dip. The photoresist will go, and wherever below that photoresist only the gold and chrome will remain. That is your last process of microfabrication, which is a subtractive process. I hope this overall view of my small visit to the clean room and overall view of equipment was useful to you. In further modules, if time permits, we will try to show you individual equipments, and that I think would be more interesting to you in this course on sensors and actuators.